Brachiopod functional morphology. And there's a little spinning brachiopod to keep us company all the time. All right, functional morphology. Let's unpack that first. This is the study of how the shape of a thing relates to what it can do. Now, this is kind of internalized. We understand this stuff without thinking about it, but it's good to think about. If you look at the skeleton, for example, of somebody who has worked out all of their life from a very young age, their bones may be thicker and stronger because of the stress, the way stress has been put on them. They respond as they grow. And so, in part, what you look like determines what you can do, but also what you do as you're developing determines what you look like. Yeah. Runners look like runners. You can tell. You can just tell. So the same thing applies to the study of brachiopods. Now here we have kind of a mystery. We have an organism, and we can try to use the organism to infer what sort of ecology it would have had, how it would have worked, how it would have fit into its environment. And so here are a couple of studies from Ryland Devert et al. And he's an expert on brachiopod functional morphology, still working today. So let's go. This is from a nice paper that they did where they had actual sort of a recirculating water trough. So they can generate a current in here with little waves. And so they can put brachiopods in this and see, all right, in what orientation would you actually be stable? Because probably brachiopods are dealing with currents like this. And so their morphology, their shape, is going to reflect this need to stay oriented in a particular direction so they can catch food as it's coming in and not get flipped over, maybe more importantly. And the easiest way to do that is to generate that sort of force and then take fossils or maybe 3D printed models of fossils and drop them in and see how these things will settle. Do they always land on the same side when you drop them in different ways? If so, yeah. Then probably the shape that they have is going to be related to this particular function, like a self-righting thing. Like the way weebles wobble, but they don't fall down if you have ancient commercials in your brain. Yeah, brachiopod shapes determine which way brachiopods will sit. So let's go look. So in order to do this, they had to reconstruct the rest of the brachiopods. Now, look at these brachiopods. They have lots of hollow spines all over the back of them. If you were to look underneath, they also have very flat little hinges. What kind of brachiopods are these? Why, they are productids, of course. Yeah, you got it. You get it. Yeah, you understand. And so here's what the productid would have looked like with all of its spines on. And there are a few specimens where people have actually found the spines so they can reconstruct what one of these things actually looks like. Pulchratia, Echinaria, Linoproductus, and Hystriculina. There's the 3D model of it, and on the other side they're showing half of the fossil of it. And so what they did was to drop these in different environments. So environments with some sand around them, environments with more like mud around them, so broken down sand, which is the siliciclastic, that's what that means. Areas that are, have a lot of oxygen, not much oxygen. So right here they're describing, based on the geology of where these things are found, where do you normally get these? So reticulaceous, they tend to be on little mounds that are a bit offshore. Things like Linoproductus tend to be in shallower water. They do not do well out more in the open sea, or maybe they need more food that you would find in closer to shore. Hard to say. Hystriculina, often found in sort of anorexic mud, so they're okay even when there's not as much oxygen. Little specialists. And some of these we don't really know. And so they took those, they took their 3D models of them, and here's our 3D model of it, and they actually put those in different substrates, like sand, and they wanted to see, all right, does it settle, correctly over time? And they found that, most of these things settle in the correct orientation every single time. A couple of them, not so much, which may mean that we don't understand the orientation. We may be incorrect on that. But then once they have settled, the sand will actually pile up around them, and the spines, even if they've been picked up and dropped into this spot instead of growing there, the spines will retain the sand and make like a little sand mound around them that will end up helping to keep them stable. And so the current may try to wash the sand out from one side, but it'll actually build up on the other sides. And so, yeah, the brachiopod will remain stable. And yeah, it will have a particular orientation. Yeah. And so here's a different study. So this is, can you recognize this type of brachiopod? It's an atropid, right? Yeah, that's all the atropids. They look like this. They're convex on both sides. They have a little flat valve on the bottom with a hole in it. That's their, they have kind of a small ventral valve. It's kind of weird in that way. Gigantic dorsal valve, gigantic arched one. That's kind of rare among brachiopods, but that's a very, and they have this crisscross sort of ornamentation. That is a very atropid way to do things, that's for sure. Yeah. So on this one, they tried to see, like, all right, this is one that does not have spines. Atropids don't have those great big spines like a productid would have. So in a place where you actually get different, what they call morphs, so different shapes of the same species. And the question is, what are these things? Are they actually distinct, or are they reflecting some kind of environmental difference? And so if you look at these, they would like to sit right about like that. That's how they like to rest on the bottom. And you can see the big difference. One has a giant sulcus, the other is pretty much flat across. They're considered the same species, but from different sites or different depths, you will get different appearances of the same species. Yeah, but all the other characteristics of them are the same. And so what they did here was they actually made a pseudo-brachiopod. And so look, they made a little lophophore. And so this one is an atropid, which remember has sideways spiraling lophophores. They glued on a bunch of false eyelashes to this one, which are going to be just like the little lophophore tentacles, so that they can check water flow through this thing, and they can check orientation, all kinds of stuff. Here it is when it's open. Here's their little virtual brachiopod. And here's a fossil where you can see inside, and you can see some of these spiral lophophore supports. And so, yeah, if this thing is there, they actually put dye inside the brachiopod, then put it in the water. And so you can see where the dye comes out. And these things will settle themselves in a particular orientation. And that orientation is going to basically end up maximizing flow through the brachiopod. So the morphology of the brachiopod will determine how it sits on the bottom. The way it sits on the bottom will end up being the way that is best suited for correct filter feeding, like maximum filter feeding. So this sort of orientation where it comes in the center and then goes out at the sides, that's going to be the most efficient filtration. It's going to lose the least of its potential food. Whereas if it comes in from the sides or other angles, it loses a lot more. It has a lot less flow coming out the other end. Yeah. So you can figure out brachiopod writing. And so the difference between these two is probably a difference where this one needed to sit a little bit more in the sediment, or maybe there's a little bit stronger current. Maybe there's less of a current here and it can stand straight up. And the orientation where they fall is going to be the one that is best suited for filter feeding. So the shape of the brachiopod determines how it filter feeds, and that determines whether it lives or dies, basically. So that's functional morphology. That's a little tiny taste. Now we'll do a lot more functional morphology when we get to the mollusks, but that is for another day. So thank you very much.